So today we're going to look at the first lesson for implicit differentiation. And what I'd like you to do first, I want you to go to Desmos, and I want you to one by one just enter these graphs in and just see what they look like. Okay. Okay, so you've looked at them, and the idea is that they're weird figures, but the question is, can we put a surfboard? Can we find the tangents at any point? And the answer is, yeah, you can see a surfboard. The problem, though, is some of these. First of all, some of these aren't functions. That's okay, because we can still find the derivative or the tangent line at any point. But the even bigger problem is algebraically, we're going to have trouble solving for y. Now, the first one, maybe you can kind of y equals plus or minus the square root of 9 minus x squared, but even that's problematic for finding the derivative because you do the positive or the negative. So the question is, do we have another method of finding the derivative when we can't explicitly solve for y? And the answer is yeah, we're going to use implicit differentiation. But before we get to that, we have to talk about two things. In this class, so I'm going to erase this. In this class, there's my okay. In this, first of all, you're going to see y equals f of x. In this class, not in more advanced math classes, but in this class, y is a function of x. So whenever you see a y, you know that it's a line, 2x plus 3. You know in this class, y equals x squared plus 5. In this class, y equals sine of 2x. In this class, y equals e to the x, y equals ln, y equals 2x plus 3 over 1 plus, x plus 5. But the idea is, once again, y is a function of some combination of x. Always keep that in mind. Once again, when you see weird letters like a's and s's and p's and q's, you're just like, no, y is a function of x. Good. Next, we need to look at this when we see dy dx. What's going on here? What exactly does the symbol mean? Well, we know it as the derivative, and I want you to keep thinking of it as the derivative, but I want you to view it a little differently. I'm going to pull the y away, so it's actually d of x of y. I want you to view d dx as an operator, and that when the second you see d dx, it means take the derivative of a function with respect to x. And we've seen that. So I could write d dx of, x squared. And you say, okay, Mr. Riley, that means take the derivative of this function, 2x. d dx, we talked about constants, 3. So you say, oh, that's 0. If we take the derivative, we learn of, x plus 3, let's say 2x plus 3 to the 5th. You say, okay, we have to use the chain rule. So this is 5, 2x plus 3 to the 4th times the derivative of this, right? Think about this slowly. If we use the chain rule, we bring the chain, and then we times the derivative of whatever's inside of there. Final answer, this is 2, so it's 10 times 2x plus 3. Now, that's a function. So you know what? Once again, so let's say if you saw d dx of y to the 5th. So you say, okay, I don't know what y is. I know it's a function of x. So just naturally follow through with the chain rule. You say, okay, this is going to be 5 times whatever's in there to the 4th times the derivative of the y. It's literally no different. Once again, we have a y, and we just don't know what it is. There's an entire course on that called differential equations, where you're not going to know what the function is until the last step. That's kind of what the introduction here is. You don't know what the y is. That's fine. Let's try another example. How about d dx of, 2y to the 3rd? So there's some function that's cubed times 2, and I want the derivative of it. No problem. So we take the chain rule, so it's 6y squared times the derivative of whatever this is. And it's written as, final answer, 6y squared times dy dx. That's the basic idea of implicit differentiation, that these y's, we can't isolate them, but we can still differentiate whatever it is we think it is. Let's go over some examples. I'm going to change the examples from the book because I have my notes. So let's say click this erase. I'm going to keep this on the board as long as I can until I can get it off. The first one, let's take a look at this. It was a circle, I believe. So let's say I'm going to just change it, maybe x squared plus y squared equals 16. This is a circle whose radius is 4. I know, because we can make a fun picture, a tangent line moves around the circle, but I can't isolate the y easily. So what I'm going to do is I'm going to take the operator into every term. I'm going to take the derivative of x squared with respect to x. I'm going to take the derivative of y squared with respect to x. And I'm going to take the derivative of 16 with respect to x. Well, the first and the last are easy. It's the second one that we have to use the chain rule. So first of all, we have 2x plus, 2y to the first times the derivative of y with respect to x. We leave this, but once again, we don't know what y is. Equals 0. Now, the instructions will be find dy dx. Find the derivative function for any point on the circle. That's okay. You just have to solve for dy dx. So we have 2y dy dx equals negative 2x. dy dx equals negative x over y. And any point on the circle has a surfboard at that point of the tangent line of negative x over y. Let's try another example. I think I can erase this now. Let's try another example. Let's try one with the cubes, because I like that one. Same idea. How about x cubed minus y cubed equals 8? Same idea. Find the derivative. We know what the picture looks like. We know that we can kind of run a surfboard along it. We know it's differentiable at every point, but I can't isolate y easily. We know from like our complex numbers unit, like y cubed is now weird. That's okay. Take the derivative of x cubed with respect to x minus the derivative of y cubed with respect to x equals the derivative of 8 with respect to x. Once again, the first and the last term are easy. We have 3x squared minus, let's figure this out, 3y squared dy dx. Once again, the 3 comes in front of the function, whatever it is, to the second power, and then we need to take the derivative of whatever that y was, is equal to 0. Let's see, we have negative 3y squared dy dx equals negative 3x squared. Dy over dx equals x squared over y squared. That's fun. Let's try shall we try the ellipse? Yeah. Let's see. X squared plus xy plus y squared equals, what was it, 10? I just added that problem in. This is a cool list. This might be something you could study for your exploration. It's known as conic sections. This is conic sections. This formula, this is an ellipse. And this is kind of cool. The xy rotates in it. It rotates it. So if you put a different number here, you can actually rotate your ellipse. That could be a fun thing. Put a variable in here. Put an a in here. And then do a slider on the a, and you watch your ellipse rotate around the axis. Kind of cool. Why don't you explore that while I erase the board? Good, we're back. Now, I know this is an ellipse, and I know that there's a surfboard along each point. What do you think? Well, let's see, the derivative of x squared with respect to x plus the derivative of xy with respect to x plus the derivative of y squared with respect to x is equal to the derivative of 10 with respect to x. The first and the last term, they're going to be the constant term. That's going to be easy. We now know how to easily take the derivative of y squared with respect to x. What's going on here? Well, this is simply product rule. Keep the first, derivative of the second, derivative of the first, keep the second, or however you do it. Well, this is 2x. What's going on here? Well, derivative of the first, keep the second, keep the first, derivative of the second. Obviously, there can be exponents here. I can make it more confusing. Plus 2y dy dx equals 0. Now, the goal is still to find dy dx. I still need to find that derivative function. So, I'm going to factor out the dy dx from these two terms. At the same time, I'm going to move this over here. Final answer, dy dx, the derivative function, or the derivative equation. Is it a function? Not really sure, but it will get me the slope of my tangent line. Is equal to negative 2x minus y over x plus 2y. Let's introduce, in the last one, we introduced some exponentials and some trig. So let's write the last problem down. Let's erase the board. What was the last problem? It was e to the x. Let's see. It was e to the x. Should I make this 2 to the x? Sorry, let's move this over. Oh, we're good. I can make that 2 to the x. I can make that 2 to the y. The books have plenty of stuff. So e to the x plus, x sine of y equals cosine of 2y. Now, we definitely knew this was not a function, but once again, we can still find the slope of those tangent lines running along it. It's weird, but it's something that exists in math, and you might be asked it, because I can just come up with any weird combination and ask you to find the dy dx. Let's go through this. We're taking the derivative of e to the x with respect to x. We're taking this product of x sine of y, it's a little new, with respect to x. We're going to have a little work to do here, no big deal. And then we're going to take the derivative of cosine of 2y with respect to x. Once again, it gets a little tedious, but we know what, you can figure this out. It's probably like, yeah, let's continue. Well, this is e to the x. What do we have here? Let's see, keep the first, derivative of the second. We're going to have to take care of this in a second. Plus the derivative of the first, keep the second. And then it's equal to d dx of cosine of 2y. Let's go on. Let's see what's going on here. Let's see. Well, e to the x is e to the x. X times the derivative of sine y. Well, the derivative of sine y is cosine y, but we have to take the derivative of whatever this y is. Plus the derivative of x with respect to x is 1 times sine y is equal to what's going on over here? Well, the derivative of cosine is negative sine. So the derivative of cosine 2y is sine of 2y, but we have to take the derivative of 2y. Let's just clean this up right here. Watch what I'm going to do. Remember, with the derivative, I can pull out the derivative of 2y. I can pull out the 2. So the final answer is 2 sine of 2y dy dx. Okay? So let's clean this up. Once again, it's just algebra. Let me erase this. Sorry. And then we're almost done. Let's see. So what I'm going to do is, you can do it your way or my way. I'm going to pull this over here and factor out the dy. So it's dy. Yeah, I'm sorry. So we have e to the x plus sine of y is equal to, so I took care of this, I took care of this. I'm going to move everything over, so it's going to be dy over dx over parentheses 2 sine of 2y minus x cosine of y. Final answer, once again, it's just tedious, it's not difficult. Dy over dx is equal to e to the x plus sine of y over 2 sine of 2y minus x cosine of y. All right? Yeah. So you found the derivative. I can ask you to find the derivative at a specific point or any algebra stuff, and that's the idea of implicit differentiation. And now you can move on. Anything else I want to say? No, we're good. And then you can move on to the next 2 videos. Here's the board. Good.